So we will be talking about critical paths in graphs, more specifically in directed acyclic graphs, or DAGs for short. I will define what they are. We will be talking about projects and critical paths in projects, which are really the bottlenecks that define how long a project may take. We will also be talking about how we find such longest paths. The way to do it will be via the so-called topological sort or linear order. And we will define all these things today and go over them and learn to use them, learn to do the topological sort, learn to find critical paths. So, well, graphs, I guess I don't have to define the graphs, so give examples of graphs. We know it from previous lectures, also from real life and what's not. Again, just a reminder that to remind you that there are two different types of graphs: undirected graphs, where the edges do not have directions, and directed graphs, where the edges do have directions, where you have arrows at the ends of the edges. And we've been looking at both during this course. So when we were talking about shortest paths and maximum flows, we were looking at directed graphs. When we were talking about matchings, vertex cover, independent set, we were talking about undirected graphs. So in this lecture, we are talking about paths, and we are going back to directed graphs. Okay, so we will be talking about directed graphs. And again, just a terminological reminder, for undirected graphs, we mostly use the terms vertices and edges. For the directed graphs, we mostly use terms nodes and arcs, even though saying vertices or edges for directed graphs is also not wrong. But still, I mean, mostly we say nodes and arcs. So let's see. One thing that we will be studying today, or which we will look at with some attention, is a cycle. So a cycle in a graph is, well, is a set of edges that forms a cycle. So this is an undirected graph, you know, like these three edges. Similarly, in a directed graph, a cycle is a set of edges such that, you know, you go along one, go along the other, go along yet another one, and eventually go in cycle, go through the first edge again. Anyway, I guess defining the directed cycle is more complicated than just, well, guessing what it is from the name. That's a cycle in the graph, and the cycle has to respect directions of the edges. So here are some examples, and I will reporting. So this is a directed cycle, green, yellow, blue. Yeah, that's true. This would not be a directed cycle because, you know, you would have to go, no matter in which way you go along this cycle, you would have to go in the opposite directions that the arrows indicate. Okay, how about this graph? Do you see a directed cycle there? Recording, yes. So this one is another cycle. Green, orange, black, yellow, red. Okay, so yeah, we can find cycles by eyeballing. Again, for a second, do you see cycles in any of these graphs? If you don't, then that's right, because this is how I drew them. In these graphs, there are no cycles, or at least no directed cycles. And the graphs like this are called directed acyclic graphs, or DAGs for short. Capital letters or small letters doesn't matter. So, well, I mean, it's the name makes sense. They are directed, so they are directed graphs. The edges have directions, and they have no cycles. And you know, the A is like this prefix saying no. So acyclic means they have no cycles. Okay, so that's the definition. A directed acyclic graph is a directed graph which have no directed cycles. I guess, again, this usual definition, well, or as in many cases, definition sounds more complicated than just the notion itself. Directed graphs with no cycles. Now, what are the examples of directed acyclic graphs? You may think of many examples, and we will have some, but one particularly relevant example of directed acyclic graphs, relevant for logistics, I mean, is the graph of precedence constraints. So you can have a project, and there are certain tasks that you have to execute in this project, and these tasks may form the nodes of your graph, and then the arrows or the edges of your graph will tell you that one of the tasks have to be done before another task is done. So again, just to do something very generic, you may have, task 1, task 2, task 3. And if you know that you have to complete task 1 before you start task 2, then you can draw an arrow from task 1 to task 3. Similarly, if you know that you have to complete task 2 before you can start task 1, then you draw an arrow, directed arrow from task 2 to task 1, meaning that this should be done before and this should be done after. And here, similarly, before and after. So on any arrow, you know that the task at the tail of the arrow has to be done before the task at the head of the arrow. Okay, so that's a general definition, but I think maybe more interesting, or at least more funny example is the one we have here on the left. I took it from CLRS, Corman, Leiserson, Rivest, and Stein. It's, well, it's about a 1,000-page book on algorithms. Well, they were saying that you should read it. I'm not sure if anybody, except for the authors, really read all the book, but it has all the algorithms. In particular, it has algorithms for directed acyclic graphs. And they use this graph as an example of precedence constraints or as a project. If you put on different garments in the morning, then, well, there are some precedence constraints. You shouldn't put shoes before you have your socks on, or else you're in trouble. And hence there is an arrow going from socks to shoes, right? You need to do socks before you do shoes. You look at any other arrow here, same thing. You need to already wear undershirts before you put on your pants. Yes, putting belt before the pants would be a bad idea, and so on. So hopefully you can understand what this graph here represents. Again, just to check your understanding and rather whether you follow or not, let me ask you these questions. Would you add any arrows to this graph? So yeah, this is a project which is called Putting On Things in the Morning, and it has some precedent constraints, and we have a directed acyclic graph. Now, I haven't checked that we have no cycles in this graph, but just from common sense, if you have a project and you have a cycle in its precedence constraints graph, then you're in trouble because you don't know from which task to start, right? In general, not talking only about this particular graph, but if you have, one task and then another task and then another task, and then, well, they don't have to be numbered in any particular order. And if you have to do task 1 before you do task 2, task 2 before task 3, task 3 before task 5 before task 1, well, where do you start? How do you break the cycle? So the precedence constraints graphs should better be acyclic. They are directed graphs and they should better be acyclic, or else you're in trouble. And well, this particular graph is acyclic. And what we can do with such graphs, with directed acyclic graphs, we can number their vertices in a special way. And right here, I have 4 graphs. And what I would like you to do now is to look at any of these graphs, anyone. You can look at this one and this one and so on. And for any of these graphs, tell me what is so special about the numbering of the graph. Can you see something which, you know, some kind of a rule, something that tells you, okay, this numbering is not just random, there is actually some structure in the numbering. So in any of these graphs, if you look at any edge, you always have the edge going from a lower number to a higher number. Or in other words, the number at the tail is smaller than the number of the head of any of the edges, of any of the arrows. And yes, this is what's called the topological sort, exactly numbering of nodes, such that whenever you have an edge from U to V, U is smaller than V. Okay, that's called the topological sort. It's also called topological order because, you know, you're ordering the vertices, you're ordering the nodes of the graph. It's also sometimes called linear order. And the reason why it's called linear order is because if you have numbered the nodes of the graph in such a way that, you know, your arrows always point from lower numbers to higher numbers, then you can lay out this graph on a line, and all your edges will go from left to right, right? So this is node number 1. I'm not even numbering these, node number 2, 3, 4, node number 5, and so on. And well, there are certain edges, you know, some nodes are connected by the edges, but if the graph is linearly ordered, then all the arrows, all the edges go from lower number to higher number, or well, in other words, go from left to right. Okay, that's the topological order. And again, just to keep it somewhat interactive, let me ask you this question. So this graph, which I've drawn linearly ordered, is, I think, one of these 4. Tell me which. Recording. So yes, this graph laid out here in the linear order is the same graph as this. Same edges between the same vertices. And I'm not going to discuss which of these 2 representations is easier to you know, to grasp. Well, linear is good because they're on a line. Maybe this one is, well, better maybe from visual perspective, but the linear order is really good for algorithms, as we will see next. Anyway, the main thing on this slide is that these graphs are topologically sorted. So their nodes are ordered in something which can be called the linear order. And it's linear because they can be arranged on a line. And if so, then all the arrows, all the edges will go from left to right. Okay, so we were able to do the topological sorting of these graphs. One good reason for, you know, looking for linear orders or in general for studying linear orders is that the linear order gives you one possible way to execute the project, right? So right here, I arranged the vertices of this graph in a linear order. I don't even have to put the arrows. I could put the arrows, you know, see what they are, but I don't have to. I know that I can execute the tasks in this graph in this order. And I will never violate the precedence constraints, because always when I'm, you know, executing a certain task, like putting on the pants, I know that all the tasks that could have led to this one, that could have had an arrow, that must have preceded this one, they are already executed. I mean, I'm not saying that all of them would have to have the arrow, like there is no arrow between socks and pants. Okay, there is no arrow like this. Well, But what I do know is that if there were an arrow from somewhere to my current task, then I know that that task has already been executed, right? We would never have an arrow going from somewhere on the right, like, oh, I should have done this task before I can do this one. No, that will never happen because I have the linear order. So linear order is good because it gives you a possible way to execute your project. In this case, a possible way to put on the garments. So as usual, I keep the videos that I used to show in class in previous years. I'm not going to show videos over Zoom, but when you have time, if you want, you can also watch some videos where they talking about direct acyclic graphs and topological sort. I mean, just other people doing that. So how do you find the linear order? So I hope I convinced you that knowing the linear order is important because, well, that's how you execute a project. So how do you find the linear order? So to find linear order, we would have to look at something called sources and sinks. And yes, I know that we had a source and the sink when we were studying maximum flows. And yeah, I mean, these are the sources and sinks, the way we define them now, they are somewhat connected to the source and sinks in the maximum flow, but we don't have to make this connection. And maybe now is one good time for me to make this joke. Well, first of all, I hope I already apologized for possibly making the same joke in different courses because, sorry, I keep forgetting which student groups I have already taught, and of course, which jokes I already told them at which points. But anyway, the joke goes that there are two problems in modern science. One is that similar things very often are called with different names. And problem number two is that the same name is used for different things. I admit it is a problem in science. I'm trying to hedge against it. I'm trying to, well, whenever we use the same notation or the same terminology for different things, trying to highlight that. But anyway, that's true. So these sources and sinks that we study today essentially have no connection to the sources and sinks that we had in maximum flow. I'm sorry about that. Quite fortunately, you will see how we use the source and sinks today, and you'll see that there is no confusion with the source and sink in maximum flow. Anyway, with all this long preface, here is the definition of a source. It's a node that has no incoming arc, so no thing like that. And similarly, sink is a node which has no outgoing arc, only incoming arcs. Okay, and well, again, I don't have the nodes colored over here, but I hope you can identify sources and sinks in these graphs. Well, here is a source, here is a sink, here is a sink. Anyway, that's not the point. The point is to convince ourselves that directed acyclic graphs do have sinks and sources, and to use them, or at least use the sources to do the topological numbering. Okay, so here is the claim. Every directed graph has a sink. Why is that? Well, here is a proof. There is only a finite number of nodes and arcs, and you can start from an arbitrary node. Is it a sink? If yes, we are done. If it's not a sink, it has an outgoing edge. That outgoing edge must end at some other node, right? Well, is this node a sink? If it is, we are done. We proved there is a sink. If it's not a sink, there must be an outgoing edge leading to yet another node. If it's a sink, we are done. If not, go to the next node, and so on and so forth. Eventually, either you get to a sink because you run out of nodes. There is only a finite number of nodes. So either you got to a sink at some point, or you have an arrow pointing to one of the nodes you've seen before, meaning that there is a cycle. Okay, so this is a simple proof that every directed acyclic graph has a sink. You go, go, go until you either hit a sink or hit a cycle. You must be in one or the other. If you have a cycle, then of course it's not a directed cyclic graph. Okay, so every directed cyclic graph has a sink. You can similarly prove that every directed acyclic graph has a source. Okay, fine. If you don't believe the proof, just believe me. Question is, how do we use the, well, let's say the sources in numbering? Remember that we want to number the nodes so that the graph is topologically sorted, so that every arrow, every edge goes from a lower number to a higher number. Question: what numbers would be okay to use for the sources? For the source, there is no incoming edge, only outgoing edges. And since we haven't assigned any numbers at all yet, why not assigning number 1 to the source? It's no harm, right? All these other nodes that we will be assigning numbers later, maybe 6, maybe 5, maybe even 2, they will have larger numbers than the source. And that's okay, because we will never have an arrow pointing to the source, pointing to 1. So we will never violate the property of the topological numbering. So yes, as was correctly said in chat, it's okay, it's perfectly safe to assign number 1 to the source. So in general, if you have more sources, more than one source, it's okay to number them with the smallest numbers. If you have 2 sources, you can number them arbitrarily with 1 and 2. If you have 3 sources, number them arbitrarily with 1, 2, and 3. That's okay. No matter how you number the remaining nodes, you will never get in trouble in the sense of the topological sort. You will never have an arrow pointing to a number 1, to a number 2, or to a number 3, because there are no arrows pointing to sources by definition of the source. Okay, so you identify the sources, so you number them with the smallest numbers, well, in this case 1 and 2. What you can do now is you can remove the sources together with the arcs that emanate from them. So forget about these. Those are numbered. Those arcs are safe. They will never point to from larger number to smaller number. Now, what remains after we have removed these sources and the arcs emanating from them is still a directed acyclic graph, right? I mean, if we remove edges from the graph, we cannot create cycles. I mean, it's still a directed graph, of course, because, well, the edges still have directions. Whatever the edges remain, they still have directions, so a directed graph. And, well, we started from an acyclic graph, no cycles, we removed edges. So, of course, we could not have introduced cycles. So this is still a directed acyclic graph. What do we know about directed acyclic graphs? They have sources. And it's okay to number the new sources, again, with the next smallest numbers, right? So we have numbered, in this case, 2 sources, or more generally, some number of sources with small numbers, 1, 2, 3, or whatever. In this case, we numbered 2 sources with numbers 1 and 2. And in this graph, we still have sources, these 2. Vertex number 3, well, now it's vertex number 3 and number 4, but this is a source. It's an isolated node, but it has no incoming, no outgoing edges. In particular, it has no incoming edges, so it's a source. This is also a source, no edge comes into it. So these 2 guys are the sources. Take the next smallest number, in this case 3 and 4, because remember, we use number 1 and 2 to number those nodes that already were removed. So the next ones are 3 and 4. You number these 2 nodes with numbers 3 and 4 arbitrarily. You could have numbered this with a 4, this with a 3. And again, such a numbering will not violate the topological order property, no matter which numbers you give to the remaining nodes in the graph, right? So the only guys that had smaller numbers, we know that they had no incoming edges whatsoever. These guys that we have just numbered with 3 and 4 only had incoming edges from the guys that were removed. guys, number 1 and 2. And all these nodes that remain in the graph, they will have edges coming from, well, either 1 and 2 or 3 and 4, but there will be no edge going from one of the remaining nodes back to the nodes that we have just numbered 3 and 4. Because if there were, then these nodes would not have been sources. Okay, I don't know if I have put too much drawing, but anyway, the algorithm is right here. So you look at the directed acyclic graph that you have at any iteration of this algorithm, identify the sources, use the smallest available numbers to number these sources, and remove the sources together with the arcs that emanate from them. Okay, and of course for sources, you only have the arcs that emanate from them. There is no arc that comes into source by the definition of a source. Well, let's continue, recurse. We still have a direct acyclic graph. Again, identify the sources. I guess in this direct acyclic graph, this is the one and only source. So, well, number it with the next smallest number, which is 5, because we have already used 1, 2, 3, and 4. Remove it together with the emanating arcs. The remaining graph, which is not particularly exciting graph in this case, it's an isolated node, but anyway, it's a graph. It's directed. Yes, it has no arrows, but it's still directed. This node is a source. It's also a sink, but it's a source. No arrow comes into it, so use the smallest available number to number it. That's it. Done. We have a topologically sorted graph. Okay, so this is the summary of the algorithm. Identify the sources, use the smallest numbers to number the sources, and remove the sources together with the arcs, and you will get a topological sort. And here are some examples, and we have 5 minutes remaining in this lecture, so I guess I will just use them to do an example on a Jamboard. So in 3 minutes, let's do some graph, and let's do a topological sort in it. So what can we do in 3 minutes? Let's do this graph. Okay, first thing is to identify the sources. Maybe I didn't make it exciting enough. Let me do it so that there is more than 2 sources. I claim that this is a source and this is a source. So let's number them with 1 and 2. And pretend we remove them. I will not erase them, so that we still see the full graph. So if these 2 guys are removed, imagine they are removed, then what will be the sources? I claim that these 2 will be the sources. So we will number them with 3 and 4. And if we remove all of these, then, well, I claim that this guy and this guy, they will be the sources. So we will number them with 5 and 6. Okay, that was quick. So that's a topological sort of a graph. I don't think we should do another example of the recording. So I have a link here to another way of doing topological sort via depth first search. You're most welcome to study it. That's how it looks like. I'm not going to go through it, but yes, there is also another way to do topological sorting by doing something called depth first search. If it works for you, then you can use the depth first search, the DFS, for the topological sorting as well. It's just as good as the algorithm that we looked at. If you want, use that one. So we know how to do a topological sort in a directed acyclic graph. Let's get back to something that we wanted to study from the beginning, finding longest path in a DAG. Or sometimes this is called the critical path, because this is a critical path for the project. It really gives you the sequence of nodes, the sequence of tasks that you have to execute one after another, and which is as long as possible in this particular project or in this particular graph. And it gives you the lower bound on how long the project execution takes. Okay, so we want to find the longest path in a directed acyclic graph. And one question that we may ask ourselves is the following. So suppose we know that this is the longest path from S to some node V. And suppose we know that the last node, last before V, so last step on this path is from U to V. Question, what can we say about this path, the path from S to U, as a subpath of the path from S to V? So we know that this path from S to V is longest possible in the graph. And it consists from the path to U plus the edge UV. So the claim is that this path from S to U must be the longest path from S to U, right? For this whole path to be the longest path from S to V, you'd better have this path from S to U as long as possible, and then you add one edge. Indeed, if there existed another path from S to U, which would be longer than this path, then this path plus the edge UV would be the longest path from S to V, and not this path. I don't know if you're completely lost in all these drawings that I made on a single path, but anyway, here it is stated in text. The subpath optimality means that the longest path to V is the longest path to the predecessor of V on the longest path, plus the edge from the predecessor to V. So again, possibly drawing it for one last time, the longest path from S to V is the longest path to this node, plus the step from this node U to node V. Okay, subpath optimality. Now, what we want to do in order to find the longest path, just as we were doing with the shortest path in Dijkstra, we will be giving labels to the nodes of the graph, and the label of the node V will be the length of the longest path to V from one of the sources. So there will be one subsource S, or node 1, whatever. Okay, so we will be again assigning labels to the nodes of the graph, but unlike with the Dijkstra, with the labels designating the length of the shortest path to the node, here the labels will designate the longest paths to the nodes. So for an example, let's look at this node V, and well, it has three predecessors, A, B, and C. And let's assume that we have already calculated the labels of nodes A, B, and C. So the label of A is 12, the label of B is 5, the label of C is 21. I don't know, there is somewhere there is this node S from which we calculate in the length of the longest paths. That doesn't matter. So the history doesn't matter. We know that the immediate predecessors of V, nodes A, B, and C, have these labels, 12, 5, and 21. Question, what is the length of the longest path from S to V? So the longest path among all the predecessors of V, among A, B, and C, is from S to C. And the length of this path is 21. That's the label of C. The label of the node is the length of the longest path to it. So if you want the longest path from S to V, then you'd better go through C. So you go through C. The longest path from S to C has length 21. You add length 1 to it, and the label of V will be 22. Because if you went, through A, then the length of the path to V through A would only be 13. The length of the path from S to V going via B would only have length 6, because the length of the path from S to B is 5, and you add one extra node, one extra edge, so the length will be 6. If you want the longest path from S to V, you should go through C, and the label of V will be larger than the label of C by 1, because we use one extra edge. These are unweighted graphs, so all the edges have weight or length 1. And yes, the length of the longest path from S to V will be equal to 22, so the label of V will be 22. Okay, so you know labels for all the predecessors of V, and L of V is really given by this formula. You look at all the predecessors, and you're looking at the largest label among the predecessors, and you add 1 to that label. That will be the label of V. Okay, so in this particular case, the label of V will be equal to 22, because the largest label of the predecessor of V is 21, so the label of V is 22. Question: in what order should we process the vertices or the nodes so that by the time we have to set the label for a node V, we would know the labels for all the predecessors of V? As we've seen from this example and from this formula, for knowing the label of V, it's sufficient to know the labels of all the predecessors of V. But we have to start from somewhere, right? We have to process the nodes in some order, one after another. And the order should be such that by the time we have to set the label for some node V, we should already know the labels for all the predecessors of V, for all the nodes that point to V. In what order would it be nice to process the vertices so that we always know the labels of everyone who precedes V, who has the arrows pointing at V? Just as a hint, in the previous lecture, in the previous hour, we actually looked at some order of vertices. We actually learned to order the vertices in some very specific order. The linear order, right? The topological sort. So if you order the vertices in the linear order, if you put them all on the line, like here, then if you process the vertices one by one, from left to right, then you know that by the time you have to process a certain vertex, by the time you have to set the label of this vertex, all the vertices to the left of it have been processed, meaning that you know the labels of all the vertices to the left of your current vertex. In particular, all the predecessors of the vertex, all the vertices that have arrows pointing at your vertex, all of them are to the left of your vertex, and they all have their labels set. So we know the labels of all the vertices that precede your current vertex, right? If this is a vertex V, And in order to set the label for it, you have to know the labels of all the vertices that point to V. If you arrange your vertices in linear order, you know that there will be no arrow coming from here. So you would be wondering, oh, what's the label of this vertex? No, this will never happen. All the vertices that point to V, they will all come from the left, and all their labels will be set by the time you process V. Okay, so if you process the vertices in the linear order, you have this wonderful property that you know the labels of all the vertices that are to the left of V before setting the label of V. Okay, so here is the algorithm for finding the longest path in a directed acyclic graph. You process the vertices one by one in linear order. So you order the vertices topologically, and then process them one by one. And to set the label of any vertex, well, you use the formula that we justified in the previous slide. The label of any vertex is equal to the maximum label of its predecessor plus 1. So again, it was probably harder to read out this formula than to understand what it is. Maybe we'll understand it on the example. So let's do the graph that we have here at the bottom of the page. So we start from, well, the very first vertex. This is our S, this is the source. And we will set the labels to all the vertices in the graph, all the vertices. And the label of a vertex will be the length of the longest path from this vertex to every vertex in the graph. Okay. Well, we have to start somewhere. We have to start from this vertex. What will be its label? What is the length of the longest path from this vertex to itself? How long a path can you find going from this vertex to itself? The length of the longest path from a vertex to itself is the same as the length of the shortest path from the vertex to itself. You don't have to make any steps. The length of the longest path from a vertex to itself is 0, and hence the label of this vertex is 0. Okay, so this vertex is done. Good. How about this vertex? What is its label? What is the length of the longest path from this vertex to this vertex? Well, of course, you can see what it is, but let's use the formula. So this is our V, and we look at all the predecessors of V. In this case, this guy is the one and only predecessor of V. The label of this predecessor is equal to 0, and we add 1 to that label. So the label of this vertex will be equal to 0 plus 1. So the label of this vertex will be 1. Okay. Again, we looked at all to set the label of this vertex. We look at all the predecessors of this vertex, all the vertices that have the arrow coming into V. We choose the one with the largest label. Well, this time there was only one. Its label was 0. We add 1 to this label, and that will be the label of vertex V. Okay, so we made one iteration. Let's continue. The next vertex, this guy, again, same thing. It has only this vertex as the predecessor. This label is 0. We add 1 to it, so the label of this vertex is 1. So far, so good. What is the label of this vertex? Again, we look at all the predecessors of it. There is only one predecessor. The label of that predecessor is 1. So we add 1 to the label of the predecessor. and get the label of this vertex. It's 2. Okay, let's go further. What is the label of this vertex? Now we have something less trivial. Again, this is our V. We want to set its label. To do that, we look at all the predecessors of the vertex V. And this time there are quite a few. So there is this one who has an arrow into V. There is this one who has an arrow. And there is this one who is the predecessor. Okay, so we have these 3 vertices as the predecessors of V. Now, out of these 3, who has the largest label? Or actually, it doesn't matter much who has the label. It does matter what is the largest label. This is the largest label. The largest label of among the predecessors is 2. And we add 1 to this largest label. And this way we obtain the label of vertex V. So the label of this vertex is 3. Again, the reason for that is that, well, here is the vertex with label 2, and it points to this vertex. So the label of this vertex should be 3. Okay. So you execute this algorithm, one vertex after another, look at the maximum among the labels of the predecessors, add 1, that will be the label of the vertex. So let's do the last vertex. This vertex has this and this as the predecessors. Here are the labels to look at and to choose the largest among them. Well, this 3 is the largest between 3 and 1. So the label of this vertex will be the label of this vertex plus 1, which in this case means 3 plus 1 means 4. Okay. So this way we have set the labels for the vertices or nodes of all the vertices in this graph, for all the graph. Just by using this simple algorithm, you process the vertices in the linear order. And for every vertex, you look at its predecessors, choose the one with the largest label, add 1 to that label. And well, this graph, as we remember, is the same as this one. So this graph that I have put here in linear order is the same graph as this one. And well, I guess by just checking the paths in this graph, you might have found the length of the longest path. It doesn't have too many edges, but when you have the graph linearly sorted, then you have a way to really execute the simple algorithm and correctly set the labels. And of course, for larger graphs, this is how you find the longest path. You do the topological sort and process the nodes one by one. Okay. Any questions about the recording? Few extensions for graphs that do have cycles. There is no efficient algorithm for finding the longest path. But if you do the source removal algorithm, if you try to do the topological sort in a graph with a cycle, then you actually will discover a cycle. Well, that's also good. You can pinpoint a problem in your project, in the tasks in your project. So we were considering unweighted graphs. The weight of every edge was equal to 1, but the longest path in weighted directed cyclic graphs can be done in a similar way. You again process the nodes in the topological order, and instead of adding 1, you add the weight of the edge. You can also similarly do shortest paths in directed cyclic graphs and even in weighted directed cyclic graphs. You can do DAGs, of course, because they work for acyclic or graphs with cycles. Yeah, you could also use this algorithm to find shortest path in a directed cyclic graph. Here is again a video which I will not play, but you can play it on your own. Yet another exposition for finding, well, actually the shortest and longest paths in a DAG. Again, if you want to look at it. Some examples. So examples of DAGs, well, we had some funny examples of putting on garments in the morning, but well, there are many cases in which the direct acyclic graphs show up, in particular as graphs of projects. So here on the right, I took a picture actually from a paper by Tobias and one of his students, where they were looking at all the processes that the aircraft undergoes during the turnaround while the aircraft stands at the gate between the flights. And well, surprise, surprise, there are certain precedence constraints among these processes. Well, I don't know, you should do cleaning before boarding or security control before repacking and whatever. And graphs like this are studied very seriously. In fact, in the airline schedule planning from an MIT course, which we will look into during the fleet, during the aircraft management course, if you take it, if you're in the FTL program, you can see I will not go into all the details, but there are quite a few things that are similar to what we do. They look at, well, they look at shortest paths, but they also use this, well, they call it acyclic directed networks. So you may see similar things that we studied in this course. Topological sort and the ways to find it. And yes, the algorithm. So what they say here is that select a node with no incoming arcs. Well, that's exactly the source that we had. So you can see they use the same algorithm. And then when they have done the topological sort, then they tell you how to find the shortest path, doing the labeling and so on. I will not go into details, but you can see how it used elsewhere. So yes, just last words. There are lots and lots of applications where actually you do have directed acyclic graphs. One place is route planning. So if you do the route planning in time, and in most cases you want to do the route planning in time, you're not just interested in the shortest path, you're interested in a path that takes as little time as possible. Then what you do is you have this sometimes called time expanded network, where you have the third action, the vertical axis, the vertical axis representing time. And then since we don't travel back in time, if you have to go from one place to another and you take the time into account, then you always travel up, right? I mean, the time always increases. We don't have the time machine, or at least not yet. There are no cycles in this network if you consider time. There would be no way that you could go from here to here, then from somewhere else to somewhere else, and then, oops, go back in time and appear in the same place at the same time. No. So these time expanded networks are really directed acyclic graphs, and finding paths in them is done by the algorithm that we studied today. Right, just a couple of examples for planning other projects. Yes, as I said, the longest path is the critical, sometimes called the critical path, because it's, well, the longest sequence of tasks that you have to do one after another. And well, it gives you the lower bound on the time needed to execute the project. Excuse me. Cycle detection, as we also discussed. If you find a cycle in your project precedence constraint graph, then you know where to look at in order to break the cycle. And here are some examples. Again, I will not go into all the details, but I have the links to the corresponding web pages where they studied different things related to project planning, and a lot of things I'm not even sure what they are, but maybe you know it from other courses. But they do consider what they call the precedence diagram method, and this is essentially the yes, the precedence constraint graph, exactly as we were discussing it. And yes, you will see that you can do different dependencies between the tasks and so on. But what you want to find is you want to find the critical path. I guess it's in red here. This is kind of the longest path. You have to do this and then this and then this and then that and so on and get to the end. So yeah, it gives you some bounds. Again, not going into details yet. Another, I guess this will be the last slide. Yeah, create a network diagrams from the tables. Yeah, I guess here on the top you have also some part of the things that you have to put on, and yeah, they sometimes break it down to right leg and left leg in the pants. Well, there is no precedence constraint. Nobody tells you which leg to put first in your pants. But other than that, well, yet another example of diagram or directly acyclic graph. And oops, here I have the link to where I took it from. Okay, no more